So here we go. What is your point estimate? Your point estimate is the proportion that landed flat in your sample, okay? So let's say that I had 10 out of 50 land flat. So what proportion would that be? That would be 20% or 0.2. All right, so you use your data, put your point estimate here. Anybody get 10? Good. One makes different than everybody else. All right, cool. Now, let's revisit the vocab. What's the population we're investigating? All Hershey Kisses. Our sample is the 50 kisses we used. The parameter, what is the measurement we're looking to find? A proportion. So we use P. It's the percent that land flat. That's the parameter. We don't know that. That's what we're trying to estimate with a confidence interval. We don't know what it is. But we have our statistics, so you're going to put your P hat right here. Mine was 20% or 0.2. Alrighty? Now, if you recall, before the break, when we did sampling distributions, we talked about 3 conditions you had to meet. Remember what they are? Anybody? That's okay. We're going to review them. All right. The first sample is, first one is it a random sample? Was our sample random? Yes. Now, the bigger question is, why does it matter if the sample is random? It's not about independence. What about bias? What'd you say, Max? Okay, so he said to eliminate bias. Can we ever completely eliminate bias? No, there's always going to be bias in there somehow. Now, can we reduce it with some strategy? Yes. We can't eliminate it, but ultimately, remember, we're trying to make a prediction about the population. If we are not careful and we don't get a random sample, then whatever result we get, we cannot draw that conclusion to the whole population. Like yesterday's example, the average number of sit-ups. Remember the bias in there? They only did athletes. So the average number of sit-ups only that they found in the confidence interval really only applies to the athletes after school. It doesn't apply to all the students at the school. Yeah? So that's why random matters. We want random so we can generalize our results to the whole population. So write that down. Second spell. We want to make our confidence interval apply to the whole population of Hershey Kisses. Alrighty? All right. Formula for calculating standard deviation of a sampling distribution of P hat. This was before Christmas break, so I'll refresh you. Formula looked like this. Does that ring a bell? Yeah? Okay, here it is. You're going to start seeing it again. It's all going to start building on each other. Now, this was standard deviation. Do you remember what the condition is that you have to check to make sure you can use that formula is?
The proportion. You gotta state your, you gotta check that it follows the law of large numbers. And that is
You're thinking of large counts.
Yeah, that one.
That's for number. That's number 7.
Gotta make it into 10%.
10% thing. The 10% thing is what allows us to use this formula, the independence thing. Okay? So what condition has to be met? The 10% condition. So we check it. What is our sample size? Okay, is 50 less than 10% of all kisses. Is that a fair assumption?
Yeah.
I think so. Yes. So we've checked our 10% condition. Our formula is valid. We can keep on going. All right? Now, here's the other kicker here. Something has changed from Chapter 7, Chapter 8. We don't know what P is, do we?
No.
That's the unknown in the question. So how the heck can we use this equation? We can't. We have to alter it with what we do have to work with. What we do have to work with is p hat, right? That's our best. So we use the formula. It looks like this, just p hat times 1 minus p hat over n. And that's what we call standard error. When we have to change it to use our samples in there instead of the parameter, it becomes standard error. Because we know sampling variability is a thing. Then it says calculate the standard deviation. So it wants you to use your p hat in this equation to calculate standard deviation. Alrighty? So your numbers are going to look different than mine. And that's on purpose. Don't just copy my numbers. You're going to need this on the next page. Alright? So when I do this, I'm going to have 0.10. Break it out. .40424. That's my standard error. Yours may be different. All right. We good? Okay, so we checked the random condition. We checked 10%, found our standard error. Now we need to address that last condition. Look at number 7. It says, would it be appropriate to use a normal distribution? We need to know if we did these samples and we dot plotted them, would it be normal in shape? But we're too lazy to do all the work, so that's where we use our large counts test. That will tell us the shape in the long run, okay? So we're going to use large counts and use your data. Again, we don't know p, so we can only use p hat. That's all we got. So 50 times 0.1. Oh no, mine's 0.2, isn't it? Oh, I did it wrong. To recalculate. So 10 greater than or equal to 10. All right, you got your numbers and stuff? Everybody passed large counts? Should. Okay, better. All right, we checked our conditions, so let's refresh for a second. Here's condition number 1. Is it random? Condition number 2 is the 10% condition. And condition number 3, is it normal? And in proportions, we use the large counts test. Alrighty? So, moving on to next page. 0.056. In a normal distribution, this is a throwback to last semester. See what you remember. In a normal distribution, 95% of the data falls within how many standard deviations of the mean? Do you remember?
2.
Very good. 2 standard deviations. That was back when we talked about the empirical rule, the 68, 95, 99.7 thing. Okay? Now, 2 standard deviations of the mean. This has to do with our level of confidence. When we calculate these intervals, this will help dictate the level of confidence, as you can see here. Now, I'm going to give you these values and then I'm going to show you how to find them. It's not hard. It's the same process every time. So here's how it works. If it's 80%, that level of confidence goes straight down the center of your diagram, if you will. If 80% is my interval, that means I have leftover in the tails, don't I? How much is going to be in the tails? What percent's in the tails? 20 total, but we got 2 tails, so that would make 10 and 10, wouldn't it? Does that make some sense? Okay, so that means the area in this tail is 10 and the area in this tail is 10%. So I'm going to use my calculator and I'm going to go back and use inverse norm. And it's going to ask me, okay, what's the area? Well, the area in the tail that I need is 0.10. And it's going to say, what is mu? And these are the standard values of 0 and sigma is 1. Alrighty, so when I do that, it's going to give me negative 1.282. Does that make sense that it would be negative?
Yeah,
Why?
because it's very small. The area and it's probably quite far from the mean, which is 0. So
The mean is 0. It's to the left of the mean, so it would be negative. That's what it's getting at, right? So what really happens when you do, these are called the critical values, these values at the ends of the interval. So this is the negative 1.282, and this makes it the positive. All right? They're just symmetrical, positive, negative. Calculator is only going to give you the negative because you put in the left tail. All righty? So it would be plus or minus 1.282. We don't use 80% very often, but the next three are the most commonly used ones. So 90% is going to be 1.645 standard deviations from the mean. 95% is 1.96 standard deviations from the mean. So notice it's getting wider and wider and wider, right? We talked about higher confidence, the wider the interval. So we're getting further from the mean. And then 99% is going to be 2.576 standard deviations from the mean. All right, we call these, like I said, I don't know if you caught this, these are called the critical values. All right, and specifically, since we're using the normal distribution, the standard normal distribution, these are z-stars. Not that that really matters at this juncture, but now it says calculate the margin of error for your 95% interval by multiplying your critical value. So, oops, it's the critical value times that standard error we calculated on the previous page. So since I'm doing a 95% interval, it's going to be 1.96 times my standard error, which was 6. This is where you're going to use your numbers, 0.0566. I'm just going to round it to 3. All right, so there's my standard, there's my margin of error. Notice the product of your critical value, standard error. Now, then it says find the 95% confidence interval for using the point estimate plus or minus the margin of error. Point estimate is our original sample data. Okay, so mine was 0.2 plus or minus what I just calculated, 0.111. So you're going to subtract and you're going to add. So if I'm going to take 0.2 and I'm going to subtract 0.111, I get 0.089. And if I add it, I get 0.311. Everybody okay?
It's from the standard error calculated in question 6.
Yes.
All right, do you have an interval? Did you find it? Okay, So what we're going to do next is look at all of our intervals, because we all had different samples, right? So here's how it's going to look. You can kind of sketch these on your paper. I'm going to start with mine. I start with my point estimate at 0.2. So this is 1, 2. So my 0.2, and it goes from 0.089 to 0.311. So it comes right here. All right, so I start with my point estimate. So I want you to kind of shout out some of yours to me, starting with your point estimate, and I'm going to graph them on here so we can see where the pattern is falling. Okay? All right, anybody got some data for me? Start with your point estimate. Anyone? Anyone?
Are you like asking?
Yeah, share with me some of your data. Like, what's your point estimate? Start with that.
Oh, okay.
Yeah, you go ahead.
0.16.
0.16 was your starting point?
Yeah.
Okay. And the low end was?
0.058. So 0.06.
Okay. And your high end?
0.26.
Okay. Arena, what you got?
0.34 is my
Starting point? Okay.
and then my lower end is 0.21,
Okay.
and my upper end is 0.47.
I'm sorry, can you say that again?
0.47.
47, okay, thank you. All right, somebody else give me your point estimate. What you got, Max?
I got 0.3906.
0.3. Okay.
And then 0.4094.
Oh, is that your low end? It must be.
You just say the 0.4.
So was your starting point, like, what was your point estimate?
0.39 was my starting.
Okay, that makes sense. Okay, we're good. Somebody else? What you got, Kendall?
My point estimate was 0.26.
Alrighty.
Wait, what do you think I did this wrong? Never mind, hold on.
Scratch that. Okay. Anyone else? Come on. What you got, Trenton?
I don't know. I think I did it wrong, but I don't know what I did wrong.
That's good. That's a good start. Okay.
Like,
Why do you think you did it wrong?
For my point estimate, I got 0.0042. Because,
That can't be your point estimate, honey.
That's why I think I did it wrong.
Yeah. We'll help you with that. Did you figure it out, Kendall? Okay, go ahead.
So my point estimate was 0.26.
All right.
The low end is 0.14, and the high end is 0.38.
Okay. Roughly there. Let's get a couple more. Anna, what you got?
My point estimate is 0.28. And then my low end is 0.15. And then my high is 0.40.
40 even? Alrighty. Let's see. Ryan, you got some data for me?
I'm not sure if this is right either. I think it's 0.551 the upper end, and then 0.329.
Okay. So would you start with like 0.4 or something?
Yeah, 0.44.
Okay. All right. Fair enough. Let's see. Brianna, do you have some data? No. Okay. Don't make eye contact. Don't make eye contact. Vivian? Come on. Lexi? Where have you been this whole period? Cassandra? Oh, Aiden? Got something different?
Yes. I think my point estimate was 0.26.
Okay.
And then what did the second?
Lower end?
My lower end, I want to say was 0.382.
It has to be lower than 0.26. Did you subtract it?
Oh, was it 0.122 then?
0.122. Okay. And then the high end was?
0.138.
Has to be higher than your point estimate.
Okay, then 0.382. That's what's got it. Okay.
Yeah. All right.
I got it now.
Beginning to see the point estimate as your center? What you got, Trenton? Are you still working on it?
What numbers go
Yeah,
where?
I'm just doing the lower end.
Okay, Chloe, you got numbers for me?
My lowest is .29, .289.
Okay,
My middle point is .4.
okay,
And then my upper is .5.
all right. Let's see, Miley? Calm. You got it? Okay, Trenton, what you got?
My point estimate was .3,
Okay,
and then my lower point was .292, and my upper point was .308.
that seems very small. Okay. All right, well, we could keep going. I could stack everybody's up, right? The idea here is, remember, we don't know P, the parameter. We're trying to estimate it. So we do a bunch of confidence intervals based on a bunch of different samples and see where they all kind of line up. And we kind of like, if we had hundreds on here, we could start to see a pattern, couldn't we? You can even start seeing one now. And that from that pattern, we infer what do we think the true proportion of kisses that land flat is. What do you think?
.28.
Based on the fact that they're kind of all falling in here?
Yeah.
Is that what we're going with?
Yeah.
Okay, so we're estimating it's about 0.28, 0.31, somewhere like that? Okay, that's pretty standard. That's pretty much the standard nationwide based on other stats classes doing the same experiment. So thousands of Hershey Kisses have been tossed. So we have a large set of data, and it all tends to reflect around 30% land on the butt flat. Makes kind of sense, right? Because they're kind of three-sided a little bit. You know what I mean? Anyway, so that's how we do a confidence interval. This is your first time to construct one, so it goes a lot faster the next time we do it. All right? Promise. So let's go next page and figure out what do you need to remember. First thing is are the conditions that are required. Got to have a random condition. Remember, to generalize to the population, it has to be a random sample. 10% condition has to be met. So is the sample less than 10% of the population? And then our large counts test has to be satisfied to show it's normal, okay? And in this case, remember, with large counts, we have to use p hat because we don't have p. Secondly, are those critical values that we use when we mathematically construct these intervals. Here you have the three most commonly used ones. Okay? You will see these so much, some of you may memorize them because they're so very repetitive. Okay? But if you don't know them, let's kind of put ourselves some cliff notes here. Okay? If C is the confidence level, we're going to put in the area and the tail in the parentheses. Okay? So it's 1 minus the confidence level divided by 2. That's how we're going to do it because we have two tails. Can you not read it?
Oh, no. I was
Thinking with your eyes squinted. Now, the formula for confidence intervals, it's not perfectly explicit on your chart. It's more like this. See how they've got it in very generalized terms? Point estimate, critical value, standard error. Because we're doing it for proportions now, but we're going to also do it for means, and we have these three things for means as well. All right? So specifically for proportions, it's going to look like this, p hat, plus or minus. The critical value we use is z star with proportions. And times our standard error, and we said that's just the standard deviation with p hat instead of p. And let's try one of these. It goes a lot faster the more you do these, so don't fret. It won't take this long. We don't have to collect data. What do you want to be when you grow up? According to a nationwide survey of a random sample of 1,000 kids under the age of 12, some kids want to be a ninja, a dragon keeper, a dancing unicorn, even an octopus. 55 of the 1,000 kids want to be a doctor.
Right, sensitive kids.
We would like to use this study to find a 98% confidence interval for the true proportion of kids who want to be a doctor. All right. So identify the parameter of interest. What are we trying to estimate here?
The proportion of kids who want to be a doctor.
So P, the true proportion of kids who want to be a doctor.
Sensitive.
Okay. All right. Check if the conditions for constructing the interval are met. There's 3 conditions, right? Let's see. Based on our question, was it a random sample?
Yes.
Yes. Okay. It's stated. And N was 1,000. I always write it for quick reference. Then we check our 10% condition. So if our sample's 1,000, is that less than 10%, of all children?
And you're really sad, right?
It's less than 10% of all children, so we can make a reasonable assumption with that. Really. All right, now the next thing is we need to know, will this be normal if we do a sampling distribution? That's where we use large counts. So 1,000. Now we need p hat. Hold up, did they tell us p hat? Well, they said 55, but that's not a percent. But if we did 55 out of 1,000, we could find it, right? So p hat, it's given to us, but we have to do a little calculation. At 55 out of 1,000, 0.055. It's not that hard to do. So sometimes they tell you straight up the decimal. Sometimes you got to do the work. All right. So times 0.055. That gives me 55. It's greater than 10. And then 1,000 times the complement of that would be 0.945. 945 is definitely greater than 10. So that is satisfied. It's going to be approximately normal. We can move on and use inverse norm and all the things. Then it says, find the critical value for a 98% confidence interval, then calculate the interval. So 98% is not one of those listed up top, is it? So we got to do the math. Over here. If 98 is down the center, what percent of the area is left over in the tails? 1% on each side. So remember, that's not just 1, that's 0.01, right? 0.01. So when I do inverse norm, it's going to ask me the area. 0.01, mu is 0, sigma is 1. And that's going to give me my critical value, also known as Z star.
Wait, why point?
Y.1.
Oh, never mind. No, I get it now. My bad.
Alrighty. Okay, when I do that, I get negative 1.282. But remember, it's positive and negative because I have a left and a right boundary, right? That's the critical value I'm going to use in my equation. What's wrong? You good? You good? Okay. What's wrong? Oh, you know why? Because I typed it in wrong. Thank you for catching that. I put in 0.10. It should be 0.01. Whew. Thank you for catching that. Thank you, thank you, thank you, thank you. Let's see. 2.32. Sound better? All right, 2.32. That works better. Or 2.33 if I round it correctly. Thank you. All right. So there's the critical value. So to calculate the interval, if you need to refresh your memory up here, the equations above, we're going to start with the p hat, 0.055 plus or minus that critical value And then I need to find that standard error. All right. So while I am shortening my decimal on my paper, I'm leaving it as a long decimal in my calculator and following through until the very end, okay?
Yeah.
Are we good? How are we doing? It's a lot of number crunching, isn't it? We can do it though. We have a calculator. We'll do this. I always start inside the radical, take the square root, then multiply by this and get my margin of error. Then I take my original, subtract the margin of error, take it, add the margin of error, and get my interval. Okay? We get there? Okay? Now lastly, it says to interpret the interval in context. How does the wording sound for the interval interpretation? You remember? The many thing is the confidence level interpretation. So good to differentiate. Interval.
You're 98% confident.
Yes, we are 98% confident that the interval from 0.0382 to 0.0718 captures the true proportion of kids who want to be a doctor. No, don't shut it down yet. I want to point out a couple things, just vocab refreshers before we shut it down. Are we okay? Like I said, it's going to go slow at the beginning, but as we do more and more confidence intervals, it gets faster. Alrighty? So when you look at your equation over here, I just want to point out that this whole thing right here, the product of these two values, is what we call the margin of error. Okay? Now, remember yesterday we were using that slider and we were talking about how if we increase our sample size, our margin of error gets smaller. Well, look at this equation. Where does sample size fall? Right here, doesn't it? So the bigger the number we divide by, the smaller all of this gets, doesn't it?
Yes.
So conceptually, we talked about it yesterday. Today you can see it mathematically. Where is it in the formula? It's right here. Okay? So margin of error is going to get smaller, bigger this gets. All right? All of this is margin of error. What was this part called? Do you remember?
The point.
Point estimate. Good. Point estimate. Point estimate. All right. A lot of vocab so far. We're going to basically do a repeat of this tomorrow with a different scenario. And then your quiz is on Thursday. So you have practice questions to start working through. Okay, you know enough to start putting a dent in those. All right, make sure you watch your videos before the day of.
Can I go to the restroom real quick?
No, it's only 5 minutes left. We can't let you go out this close. Sorry.
I need to change.
Well, you just changed clothes in my class.
I didn't shoot my pants.
Oh, that's on you, Shmoo. You can do it on the way.